Hey, how's it going?
It's tiring. Got a senior design competitions this weekend,
Oh, dang.
and I gotta finish the midterm beforehand. But it's basically just it's just the model itself, right? Nothing extra.
Yep, just the model. Yep, path segmentations and model.
Yeah, I went and looked through it. I saw mine. It would be good. Let's just hope my PC works. But it should be good. Oh, so it doesn't. Yeah. They do it right now. That was all it. Yes, yes. Oh, so it's just an intro project. Yeah. What's the release? Can you pop that into the building? That are just awesome. I don't know if it's just for the printer setup or if someone was ripping on the learning. Yeah, I suspect is that the spot where it has the issues is right where it's right where people print. So without a doubt, probably that fucked up the entire brain machine.
It's like you can't because it becomes so person. You can't print on the left side, you print on the right side.
Alright, so
Right side, like towards the outer edge, like it's fun. I mean, it's necessary. Yeah, so really sad.
wait, who messed it up?
I didn't even touch it. And that was ages I did the print on That's why I didn't touch it.
I know.
If I didn't know how to do it, I'm like, all right, I'm good.
Well, I remember they're asking me how to put the fucking machine in their slicer. I'm like, huh.
Yeah, the only thing that's even for having, use color print.
Yeah, to clarify, for the mental project, we have a tomatoes model, right? Yeah.
I'm not saying.
But I mean, I want the whole project, but yeah, you just have to get up to the model portion.
The model portion?
Yeah. We're gonna do another workshop next week to do the meshing and the simulation.
Okay, for sure. Yeah. Thanks, I saw that part and I didn't know we were going.
Oh, not yet, yeah.
Really? Yeah, well, and saved your asses. You know who was supposed to say that watch? Oh, David was? There's only one person in that whole shop that has that title, and they would be unnamed. I know exactly. It's not from Pearl. Well, you guys are watching soccer all of the morning. No, it's happening.
Well, David continued the print. Like I said, I have certain things that you see. No, I'm not. No. It's just like.
Brand new.
Yeah. Wait, how do you literally? It's like silence.
It doesn't even have.
So it will just somebody probably like.
Doesn't have levelers, it's two linear rows, so yeah, I got that.
My eyes more than stress. Look, there's a.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? Good spring break, hopefully.
Oh, yeah.
Good, bad, too short, all those things. Well, it's over now, so we got to go back to work. So we are in the final stretch of the semester. So we have 5 more weeks remaining. So we have this week, next week, the week after, and 1 more week after that. And so it's going to be packed. And so we have kind of a busy final 5 weeks here. So we have a midterm exam we need to do. You guys have a project due this Friday, and then the final project after that will be due after that. Okay. So we have quite a bit to do, but we'll kind of take it just one step at a time from here. But yeah, things are going to ramp up a bit in class. Okay, so one thing I want to announce, just because just kind of talking to you guys, and I know there's kind of a lot going on with senior design, and I know with grad students kind of have a lot going on this week too. I am going to push the due date back for homework 3. So homework 3 was posted kind of right before we left for spring break. Originally it was due this Friday, together with the with the project. But I'm gonna push back the due date for homework 3 until next Wednesday, April 17th, until 11:59. So I wanted you guys to turn it in kind of before the midterm exam, which is gonna be the week after that, so we can push it back to next Wednesday with no issues, so. So homework 3, just to give you guys a little bit more time to work on, is gonna be due next Wednesday as opposed to this Friday, so you have a little bit more than a week to work on it from here on in, okay? Okay, and so with that, this week, what I have planned is a topic on velocity distributions. And so we're going to talk about the Wormersley profile, the Wormersley number, what that means, and a little bit of the mathematics behind it. Okay. So I want to be clear just straight up. So what we cover this week is not going to be on the midterm exam. So actually up to this point, from this point forward in the class, a lot of what we're going to do is going to be two things. And so one, we're going to be covering kind of a lot of the gaps, just kind of working our way up to kind of CFD and the final project. So the topics we're going to cover this week kind of fall into that category. So I'm not necessarily going to test you on the things that we're going to go over this week, but it is kind of important just for the development of when we get to CFD, so you understand kind of more of the context and some of the settings that we're going to go over next week. The other things that we're going to go over from here on out is kind of more information on the final project. So we'll be going over computational fluid dynamics, what that means. And I know some of you are already within, you're already taking 336, which is the CFD course. And so you'll see a little bit of overlap in terms of the content for here. We're obviously not going to get into the weeds of the details and the math, but more we're going to talk about how to set up the equations or set up the simulations and kind of what all the different settings mean and kind of just a little bit of theory on that. Okay. So that's kind of where we're going to go. So, on the one category, we're going to be covering content where, it's useful to know, it's interesting to know just within the context of this whole class. I'm not necessarily going to test you on it though. The other category stuff that we're going to cover is stuff that's directly pertaining to the rest of the final project, which we're going to talk about next week. Okay. All right. Yeah, so besides that, I did, there were quite a few of you that emailed me over break about your final project, so it sounds like those are going well. If you're running into issues with the final project, you don't know where to start, or if you want me to look at some certain parts of the model that you're not sure about, definitely shoot me an email. So I'm happy to look at your model over email and give you some tips. Or I have office hours on Thursday that you can come to as well and have me look at your model as well. Okay. But I do know that some of you have turned it in already, which is good. But if you haven't started yet, I would definitely, at least open up some vascular today, because some models I think are easier to make just based on the image data, but some can be quite challenging. So you want to make sure that you at least know a good scope of kind of what you need to do to complete the midterm project for this Friday. Okay. Because starting next week, we're going to be working directly with that model. We're going to be learning how to mesh it, how to set up the simulation, go from there. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started with the content for today. So again, what we covered today and what we covered Thursday, not going to be on the midterm. We're actually already finished with all the content for the midterm exam. But it's just kind of good to know. Okay. All right. So the topic for today is called oscillating flow in a rigid vessel. Okay. So before spring break, we spent about 3 weeks talking about things like 1D equations and impedance in blood flow, right? So that all kind of constituted what I consider to be 1D model. Okay. And even before that, we covered lump parameter modeling, which was circuit representations, which I consider to be like 0D. Okay. So of course, the next logical thing is 2D model, right? And so that's going to be the topic for this week. Now, as we kind of work our way up the geometrical complexity, as we work our way up the dimensions, there becomes less and less that we can do actually by hand, right? So the most calculations that we can do by hand was in the lump parameter modeling. So we were able to form those differential equations, and we're able to basically get solutions for them. In 1D modeling, if you recall before spring break, we spent quite a bit of time deriving the equations and understanding kind of where those equations came from. But in terms of actually solving those equations and getting things that are useful, we're kind of extremely limited. And in fact, we could only really get solutions when we solved it in a computer. Okay. So 2D modeling kind of follows that same trend. And so, there's kind of limited kind of usefulness that we can actually solve by hand, but there's still kind of some very important concepts to know. And hopefully I think what we learn today can kind of, give you a little bit more context to your fluid mechanics courses as well. Okay. And that's kind of the whole purpose. So that's kind of my whole kind of goal with going through all these different modeling methodologies, right? So, with the 0D modeling, with the 1D modeling, with the 2D modeling, there are some points and some places where we can get an analytical solution. We can actually solve things by hand. But, the reason we're going over these methods is not, the methods themselves are important, and it's important that you guys know, but ultimately what we're working our way up to is we're working our way up to 3D simulations, full computational fluid dynamics, just so you can understand kind of contextually and physically kind of what's going on in those CFD simulations and how to interpret your results. Okay. So in other words, the most important thing is that we're building intuition. We're building kind of our physical kind of understanding of what's going on. Okay. Okay. So with that said, we're covering something today we saw a little bit of kind of in the very early parts of the class, which is the velocity distribution. Okay. So let me go ahead and draw our vessel here. So I'm going to draw kind of a contained flow. Okay. So what we're seeing right now is kind of a sideways cross section of the vessel. So the blood is flowing from left to right. Okay. And what we're interested in this week is particularly how does the velocity distribute itself throughout the vessel cross section. So we've already solved this problem already in a very kind of specific case, right? And so if you think back to kind of the very early parts of the course, and so when we did our review of fluids, right? When our flow is steady, right? So we have steady. So nothing is changing with time. When our flow has rigid walls, okay? And another assumption that we'll talk about a little bit more today is when the flow is fully developed, we solve for the velocity distribution in this case by solving the Navier-Stokes equations. And that's essentially what we did kind of in week 3 of the course, right? We took our Navier-Stokes equations, we canceled a ton of the terms because of our assumptions here. There were a few other assumptions, like we assumed that the flow was axisymmetric and things like that. But essentially, we canceled enough terms in the Navier-Stokes equations that we could solve it by hand, we could solve it by direct integration. And what we found was that under these conditions, we obtained what's called the parabolic velocity profile. Okay. It gets the name parabolic because the velocity distribution visually looks like a parabola. Okay. And we know that a parabolic function is a quadratic function. So we have our uz of r if dependent on r squared. Okay. So visually it looks like this. And so if we go to the vessel cross section here, a parabolic velocity profile looks something like this. And in fact, this particular solution to Navier-Stokes has a name. It's named after the first dude to do this, and it's Poiseuille flow. It's French people and their names is so hard to spell. I had a colleague that always called it Poiseuille flow, which I don't think is correct, but I don't know if Poiseuille flow is correct either. So, I think only a French person can tell the truth there. But this parabolic solution is credited to Poiseuille. Okay. So that's what we know so far. So that's what we've been able to do based on just Navier-Stokes. And so so the question is, if we already have this solution, so if we already know that the profile is parabolic, then what more is there for us to do, right? Well, what the next step is to take our assumptions here and to basically relax them, right? Because we know for sure that all 3 of these conditions are not necessarily satisfied within the cardiovascular system, right? These 3 assumptions were just kind of convenient for us when we were making our initial solution. All right, so what we're going to do this week is we're going to relax just one of these assumptions, actually, and we're going to see how that affects our solution. Okay? You'd be surprised. So even just relaxing one of these assumptions is going to lead to a much more complex situation. Okay, and the one assumption that we're going to relax, and maybe you picked up on it just based on the title of the notes here, is the steady state assumption. So for this week, we're going to get rid of the steady state assumption. We're going to include that time derivative in the Navier-Stokes equations, and we're going to see how that affects our velocity distribution. Okay. Out of those 3 assumptions, that seems to make the most sense to get rid of first, because even though we know that there are blood vessels are deformable walls, there are some regions where the walls are pretty rigid, and even the deformability is still pretty mild. The one that's going to have the biggest effect is the pulsatility, because we know that blood flow is very pulsatile in nature. It ebbs and it flows depending on where the heart is contracting or relaxing. Okay, so it makes sense for us to get rid of the steady state assumption first. And then the others, we can relax at another time. Okay. So that's kind of where we're going, and that's kind of the motivation for this week. Okay. Any questions on this? Okay. All right. And what's interesting about this is that, one of the reasons we made all these assumptions to begin with is that, we made the argument that we wanted to get a closed form solution to Navier-Stokes, which is normally very difficult to do. It turns out, when you relax a steady state assumption, you can actually still get a closed form solution to Navier-Stokes. It's just that you need to use a little bit more advanced mathematics to get there, rather than just kind of basic differential equations. Okay. But as always, we have to start with our assumptions. So two of these assumptions are kind of listed up above, but I did want to expand on them and kind of talk about one more assumption as well. So one assumption that we're going to make is the rigid wall assumption. And so the rigid wall assumption basically assumes that our radius is going to be fixed or constant. Because in a deformable wall case, we've seen in the 1D equations that that wall can move, and so ultimately that changes the radius, or the radius of the vessel can change with time. Okay, but when you assume rigid walls, then our vessel radius is going to be fixed. Okay. This also means that our velocity is going to be purely in the z direction, so we're not going to have any radial component of velocity at all. Okay? In other words, our velocity is going to be just purely in the z direction. Okay, number two. The second assumption that we're going to make is that the flow is fully developed. And so the fully developed assumptions essentially means that we're going to ignore any changes in z. Okay. Okay. So if you think back to fluid mechanics, a fully developed flow essentially means that, it's no longer developing, right? And so if you kind of remember from fluid mechanics, the concept of a boundary layer and things like that, right? So when a flow first enters kind of a space, there's kind of a boundary layer phenomenon or an edge effect phenomenon that occurs. And so we're going to ignore those effects. And so we're going to assume that the flow doesn't change in the z direction. And so essentially this means that any derivatives with z, we're going to say is approximately equal to 0. Okay, so that's going to help simplify. It's going to help simplify a lot of the convective terms in our equation. The third assumption, or the third important assumption that we're going to make is that we're going to ignore any changes in theta, right? And so we're going to start with our Navier-Stokes equations in cylindrical coordinates. And so, in cylindrical coordinates, we have that theta direction, the polar direction. And so we're just going to ignore any changes in that direction as well. So anything partial theta is also going to be equal to 0. You would really only have changes in the polar direction if you have any kind of twisting or vortical flow, which can happen. There are certain parts of the cardiovascular system which do have it. Some of you will have it in your projects, But just for simplicity here, we're going to ignore it. Okay, so we're going to consider it just purely as a 2D case. All right. And so with those assumptions, I'm going to skip kind of the labor of kind of canceling the terms, but I'm going to show you kind of the Navier-Stokes equations that result from this. So we have partial UZ, partial T is equal to minus 1 over rho, partial P, partial Z, plus nu partial squared UZ, partial R squared, plus 1 over R, partial UZ, partial. Okay. So it's actually very similar to the Navier-Stokes equations we worked with in the steady state case. The only difference is that we have the addition of this term right here. Okay. So this term right here is our unsteady term. But you'll see very soon that this term changes everything. So instead of solving this as an ordinary differential equation, we're going to solve this as a partial differential equation, which is a lot more challenging and requires kind of much more advanced mathematics. All right. Any questions on this so far? Okay. All right. All right, so this is our equation here. This is what we're going to be solving for. Okay. So to find an absolutely general solution to this equation is actually very, very difficult. And so we're going to look for solutions in a very specific space based on what we know physically about our system. Okay. Okay. So basically, since we know that in the cardiovascular system, we have pulsatile flow. The thing about pulsatile flow is that it oscillates up and down, right? So it's not just going to be any kind of generic unsteady function. We know that the time behavior is going to be some kind of oscillation, which is going to be a sine or cosine, right? And so we've seen this, right? And so if we look at things like the pressure or the flow rate, we know that it kind of has this characteristic to it. Okay? So there's kind of a periodic nature to the function. Right. So that's really nice. And so, instead of solving it within the space of all possible functions of t, now we can just look for the periodic or the oscillating functions in time, which we already know kind of a very nice family for that, which are the sine and cosine functions. Okay. we've already taken advantage of this, and so, we've already seen a situation in impedance, where we assumed a periodic solution, right? And so we're going to use a very similar technique here. So hopefully that'll be familiar to you. Okay. All right. So let's go ahead and apply this. And so applying this methodology, we can assume that our pressure gradient, our forcing term, is going to, oscillate up and down like a sine. Okay, so mathematically, that's going to look like this. So in our Navier-Stokes equations, we had a term. We had partial P, partial Z. Okay. So that was our forcing term in Navier-Stokes. What we're going to assume here is that this is going to be equal to A times. And so we're going to go with the as generic of a sinusoid as possible. So we have cosine of omega t, where omega here is the oscillation frequency, plus I sine of omega t. Okay. So it's a combination of cosine and sine terms. And I added that imaginary number there for a very particular reason. And that's mostly just to help us with the math a bit later to make it a bit cleaner for us. Because this summation here is nothing more than our Euler's equation, which is e to the I omega t. Okay. So remember, we made use of that last time in before spring break when we were finding solutions to our impedance equation. Okay. And so that means our e to the I omega t. Excuse me. So our pressure gradient here is going to be A. A is some unknown coefficient at this point, multiplied by e to the I omega t. And this form is really nice because when we take derivatives of this with respect to t, that exponential is going to come out. And so it's going to allow us to kind of simplify and make our solutions nice and cool. Okay. All right, so by that same token, logic, our velocity solution is also going to have that same character. In fact, what we're going to assume is that our velocity solution is completely separable. And so we have an R component and a T component, and we're going to assume that they are completely separable from each other. We have UZ, which is a function of R and T. Okay. So that's ultimately what we're going to be solving for. This is going to be equal to e to the I omega t. Okay. So that's the oscillating component. That's the unsteady component of the solution, multiplied by the spatial component, which is just in this case is going to be R. So we have U of R. Okay. So this right here is the unsteady component. This right here is the spatial component. Okay. All right, so what we have here, based on these assumptions and based on these forms, we have a very classical kind of separation of variables type of PDE. Okay, so we've done this, we've done this a few times before, mostly in the last few weeks. And so the next steps is just to take these assumed forms and plug them into our Navier-Stokes equations and kind of work through the algebra, work through the calculus of that solution. All right, so that's where we're going to be going. And so, I wanted to pause here kind of before the math gets here. Right? Any questions on just the logic of any of this stuff, or just any questions on what we've done so far? Okay. All right, so let's get into it. So let me write down Navier-Stokes again, just because just so we can work with it. Okay. So when I say that we're going to plug into Navier-Stokes, we're going to plug into this guy up here. So Navier-Stokes equations is partial UZ partial T is equal to minus 1 over rho partial P partial Z plus nu times partial squared UZ partial R squared plus 1 over R partial UZ partial R. Okay. So that right there is our Navier-Stokes equation. So we haven't done anything to it yet. So all we've done is we just used assumptions to kind of get to this form here. Now, basically everywhere that we see UZ, okay, so we have UZ here, we have UZ here, we have UZ there. Okay. Everywhere we see UZ, we're going to plug in our assumed solution. Okay. We're going to plug this in here, plug this in here, plug this in here. Okay. The other thing we have to plug in for is partial P partial Z. Okay. Right, so we're going to plug in for that. And what we're going to plug in is what we have up here. We have EAE, the I omega T. Okay. All right, so this next step is going to seem like a lot is going on, but just know that we're just plugging in for these quantities, and we're just carrying out the derivatives. Okay. But because our solutions kind of take the following form, our derivatives are going to be easy to carry out. And that was the whole idea, is to make our derivatives easy. Okay, so let's plug in. So we have partial UZ partial T, so we have partial T of e to the I omega T times U of R, okay, is equal to minus 1 over rho times partial P partial Z, so that's going to be minus A over rho e to the I omega T, okay, plus nu partial squared partial R squared of e to the I omega T U of R, okay, plus 1 over R partial R of e to the I omega T U of R. All right. So all I did in that step was that I took everything that's highlighted in the line above and I just plugged in our assumed forms, right? Whether it be our velocity UZ or our pressure gradient partial P partial Z. Okay. Okay. So let's carry out these derivatives. And so these derivatives are quite easy to carry out because of our form here, right? And take note, whenever we're taking a derivative of T, then we can ignore every term that has to do with R. And when we take derivatives of R, we can ignore every function of T. Okay. So for example, when we take the derivative of this first term right here, partial T of e to the I omega T U R, we end up with derivative of e to the I omega T, which is I omega e to the I omega T. Okay. And then that last function there, U of R, that's not a function of time. So we can just kind of carry that through. So that just just becomes kind of a straggler that kind of comes along with the process. All right, next term, our pressure gradient term, this stays the same. There's no derivatives to take here. Okay. All right, next we have our viscous term. So first we have the second derivative. And so we're taking a derivative with respect to R. We're taking it twice, actually. So the e to the I omega t is just a constant in that case. It doesn't depend on R. So we can just factor it out of the derivative. Okay. And then we have partial squared, partial R squared of U of R. Okay. And so since that U of R is just a function of a single variable, we can change these derivatives to regular derivatives. So we have d squared U dr squared. Okay, and then our last term there, we have e to the I omega t over R times du dr, first derivative. All right. Let's simplify this expression before we move on. Okay. If you notice here, after we carried out all the derivatives, every single term has an e to the I omega t, right? So that's something that's present in all four of our terms here. Okay. And so if that's the case, we can factor it out. Okay, so we can kind of factor out all those terms and cancel them all. Okay. So that's nice. Okay. So after we cancel this out, let's do a little bit of bookkeeping. So what I'm going to do is I'm going to divide the whole equation by nu. Okay. So we're going to divide our entire equation by the viscosity. Okay. And then what we're going to do as well is we're going to move every term that has u in it, and we're going to put that on the same side of the equation. So we're going to keep it on the right side, basically. All right. And so if we do that, we end up with the following. And so we have a positive a over rho, or excuse me, a over rho nu. Let me keep it all on one side for now. And so if we move this u of r term to the other side of the equation, we have 0 is equal to minus a over rho times nu plus d squared u dr squared. Okay. So part of the reason I did that is because we can see here that we have our second order derivative term, that's our highest order derivative. And so I want to keep the coefficient in front of that term 1. Okay. Plus 1 over r du dr minus I omega over nu u minus a, oh, I put that already. Okay. Next thing we're going to do here is we're going to non-dimensionalize all of these terms. So we're going to make them all kind of non-dimensional. Okay. So the way we're going to do that is we're going to take this equation and multiply the entire equation by r squared. So if we do that, we get 0 is equal to minus a r squared over rho nu plus r squared du dr squared plus r du dr minus I omega r squared over nu times u. All right, so the reason we're putting it in this form will be kind of clear later. Okay. Or let me give you a sneak preview. So, what we have here is we essentially have an ordinary differential equation, right? So we've taken our partial differential equation, and we now have a differential equation in only one of the variables, which is r, okay? And we want to find a solution to this equation, okay? The thing that makes it difficult is the presence of all of these kind of r terms here, okay? And I know what you're thinking. So, we kind of made it worse in the last step by multiplying by r squared, right? But there's kind of a reason that we're doing this, because any type of differential equation that has these r terms here that's non-homogeneous, which is what we have, is actually very difficult to solve. Okay, but there is a trick. The trick is that if we can get this, if we can kind of massage this equation, if we can kind of manipulate it in a way so that it matches a certain canonical form. Okay. A canonical form is basically a form of an equation that's been solved many times before in the literature. Okay. And so if we can manipulate this equation to get into that form, that we can kind of skip to the solution. So we can say that, oh, this looks like an equation that's been solved before, and so this is the solution that we can do. Okay. In particular, the canonical form that we're kind of aiming for, that we're kind of shooting for, is something called a Bessel's equation. So Bessel is another kind of ancient European mathematician. And so what he was able to do was he was able to solve a differential equation kind of this form, you know, and kind of document his results. Okay? And so if we can get this equation, it's not there yet. And so we can get this equation into that kind of Bessel's equation form, then we've basically going to solve our problem. So it's kind of a cheap way. So, some people don't like it. I know I didn't like it when I first learned this because it feels kind of cheap. And so, instead of actually solving the equation, we're kind of dancing around it. We're kind of, just manipulating its form until we get something that's convenient. But in this case, this kind of is the best way to solve this equation, because we can go into Bessel's original thesis, and we can follow his method, but that would kind of change the character of the class. And so so this would no longer be an engineering class. This would be very much like a math class. And so, we're going to do what most engineers do. We're going to find kind of the most convenient solution, which often means kind of relying on something that someone else has done before. So, yeah, this kind of really is the fastest, kind of easiest way to solve this equation, just to manipulate it, through a couple change of variables to get into that. All right, any questions on this so far? Okay, so that's where we're going, or that's what we want. And so let's kind of take the next steps to get there. All right, so the first thing we kind of have to eliminate here is we have this imaginary number here. We have this I that's kind of like a source function, right? So let's deal with that first. So let's perform a change of variables. Because right now that I is kind of in the way. Okay. And because if you kind of notice here that there's kind of two groups of terms that we've created in our equation. And so on the one hand, we have all of these terms here. So all of these terms are the u terms, right? So they involve our function u or our solution u and its derivatives. Okay. The other term that we have here is this one, which if you kind of recall, if you kind of look back on your notes, this term came directly from our forcing term. This term came from our pressure gradient. Okay. Okay. So one of the things that's making this difficult to solve right now is we have this kind of ugly imaginary number kind of in our u terms. So let's see if we can kind of move it out from there first. Okay. So the way we're going to do that is we're going to perform a change of variables. And so we're going to define this new variable x. And x here is going to be equal to I to the 3/2 times r times square root of omega over mu. It seems really random, but we're taking this form just to kind of eliminate that I from our u terms. Okay. Okay. So we're performing a change of variables on a differential equation, right? So we have to be a little bit careful here because when we're performing such a change of variables, we have to update all the derivatives as well. Okay. Because essentially this new function x or this new variable x, that's now going to be our unknown, right? Or it's going to be our new independent variable. So that means all of our, everywhere we see r, we're going to plug in for this obviously, but then everywhere that we have a derivative in r as well, right? So we have partial r squared, partial r, okay? We're going to plug in for that as well. So we need to use a little bit of chain rule here based on our change of variables to see how our derivatives are going to change. Okay. So we actually have two derivative terms that we need to satisfy here. So we have an r squared du d squared u dr squared, and we have an r du dr. So let's start with the r du dr first. So we want to update this to match our new variable x. Okay. So let's break this derivative up using chain rule. And so if we do that, we have r times partial u partial x multiplied by partial x partial r. Okay. So that partial u partial x, that's what we want. That's the derivative that we want. But we also need to plug in for partial x partial r. Okay. And to do that, we're going to plug in just our direct, we're just going to plug in our change of variables in here directly. Okay. So we have r partial u partial x times partial r. And we're just going to plug in our expression for x here. So it's going to be I to the 3/2 times r times square root of omega over nu. Okay. Okay. So let's go ahead and take the derivative of that last term there with respect to r. And so luckily, this is just a linear function of r. And so the derivative here is going to cancel out with that. Okay. And so when we do that, we get r times partial u, partial x, or I should just say du dx, multiplied by I to the 3/2 times square root omega over nu. Let me rearrange this term a little bit just to make it a little bit more clear. And so this is going to be I to the 3/2 multiplied by r multiplied by square root omega over nu times du dx. Okay. So all I did for that last line there was that, because all these terms are just multiplied by each other, the commutative property of multiplication, you can rearrange the order. Okay. All right. So the reason I did that is so that we can group these terms together right here. So everything in parentheses right there, if you'll notice, is actually exactly the same as our change of variables here, right? So everything in the parentheses here is just going to be equal to x. Okay. So that's good. And so when we perform our change of variables, what we had originally was r du dr. We just end up with x du dx. So in this case, it ended up kind of being a simple result, but it was nice to kind of go through the chain. It's always good to remind ourselves of chain. All right. Any questions on that? Okay. All right. So for the second order derivative, I'm gonna spare you guys the chain rule for that. But for the second order derivative, okay. So if you look back at our equation here, our second order derivative is r squared d squared u dr squared. Okay. Right, you can go through the same kind of logic as we did there. We can use the chain rule and everything, but what this is going to transform into when we change it to x is going to be x squared d squared u dx squared. Okay. Okay. Finally, we have the last term. Okay. And so that last u term was a minus I omega r squared divided by nu times u. Okay. This was the last term involving u in the equation. Okay. And it's the whole reason we're doing this change of variables to begin with, is so we can eliminate I from this term here. Okay. All right, so let's plug in for r. So let's go ahead and apply our change of variables. Luckily here, we don't have any derivatives, so we don't have to do any kind of chain rule. Okay. So we plug in r in that case there. So we have a minus I omega over nu times r squared. Okay. So we know that our r has the expression of I to the 3/2 times or excuse me, let's plug in the inverse of this. And so when we plug in for this, we plug in for r squared. R squared is going to be let's do this from the top. Let's take our expression for x and then find out what r squared is. So that x is equal to I to the 3/2 times r times root omega over nu. So let's solve this equation for R. So if we solve this equation for R, we get R is equal to X times square root of nu over omega times I to the minus 3 over 2. And then we square it. R squared is equal to X squared times nu over omega times I to the minus 3. Okay. Okay, so let's plug that in. So we have X squared times quantity nu over rho times I to the minus 3. So I to the minus 3 is same thing as 1 over I cubed. Okay. Times U. All right, so all I did there was I solved for an expression for R squared and I plugged it into the expression. Okay, so let's go ahead and simplify this. So on the outside there, we have an I. So that I is going to cancel out with one of the i's in the denominator. So we're just going to end up with I squared on the bottom there. Okay. We have nu. The viscosity is going to cancel out with that. And then we have the frequency omega. It's going to cancel out with that as well. Okay. And so what we have is we have minus X squared over I squared times U. Okay. From here, it actually simplifies quite a bit. Right? Because I squared, so I here is our imaginary numbers. We know I is equal to square root of minus 1. Okay. And so I squared is just equal to minus 1. And so if we have minus 1 up top and minus 1 on bottom, and so what we end up with is X squared times U. Okay. All right, so that's the reason why we chose our change of variables the way we did, was to kind of simplify that term tremendously. Okay. Okay. So now we can plug all this in. And if we plug all this in, and there's one more R squared term we have to plug in for as well, which is the A term here, the forcing term. Okay. But that's simply just kind of plugging and chugging in. So I'll let you guys confirm that. Okay. But by doing this, we've kind of dramatically simplified our U terms here. Okay. So after plugging all these in, we get X squared d squared U dx squared plus X du dx plus X squared U is equal to X squared times A divided by I rho omega. All right. So it was a lot of math kind of substitution, but hopefully, again, this is one thing where, the details of kind of what we did, not, they're important, but, not something that, I want you guys to memorize or kind of memorize every single step. But hopefully you guys kind of understand the logic of kind of why we did that. Okay? Because what we've done, through that change of variables, is we've simplified everything on here, okay? So what we have on the left-hand side now is a very kind of clean expression, which just, our solution variable u and our dependent variable x, okay? So this right here is very close, right? And so by doing this change of variables, this whole thing is very close to a Bessel's equation. We just have to make one more kind of small adjustment. But we'll get to that in the next step. All right, any questions on anything that we've done so far? Okay. All right, so the only thing here that's kind of preventing us from, from saying that this is a Bessel's solution is actually this guy right here. So if you think back to your terminology from differential equations, you should know that this term here is what we call an inhomogeneous term. Okay. Inhomogeneous terms in differential equations play a very crucial role. And so they play the role of what's known as kind of our forcing, okay? And so if you kind of trace back kind of the origin of this term came from our pressure gradient, which is essentially our forcing term in our Navier-Stokes equations, okay? But right now it's an eyesore, and so we need to kind of get rid of it in order to solve our Bessel's equation. Well, luckily for us, there's kind of one more change of variables that we can perform. It's a very short one, don't worry, there's no derivatives involved to kind of get rid of that inhomogeneous term. Okay. So the change of variable that we're going to do, so instead of changing the independent variable, we're actually going to change our dependent variable. Okay. So to make this one last change of variable, so we define a new variable y, and this is equal to u minus a over I rho omega, okay? If we plug this in, everywhere we see u, this will eliminate that inhomogeneous term. Because the change of variable that we're doing here is something called like an offset, right? So it's a very common mathematical trick that you can use to get rid of certain terms. Okay, and the reason we can do an offset, and we've kind of been setting this up from the beginning, is that if you notice our inhomogeneous term has this x squared. Okay, that's the exact same x squared that we have on this u right here. Okay. And so if we perform just a simple offset on our solution here, then that kind of gets rid of both of those terms. Because as soon as we plug in for y, it's going to absorb that inhomogeneous term into there. Okay. And the nice thing about an offset is that when you take its derivatives, then that offset goes away. Okay, because this offset term right here, okay, this offset is just a constant offset. So when you take its derivative, it just goes away. Okay. Okay. So it's something that we're doing at this point. It seems very simple, but it's something that we kind of set up from the very beginning. And so, this proof, it's, hopefully it's not as long and as tedious as kind of the proofs we did before. But I like this proof a lot because it's, it's something that we've kind of set up from the beginning, and we're kind of reaping the fruits of our labor at this point. Okay. Okay. So by doing that, our final equation becomes we have x squared, d squared y, dx squared plus x dy dx plus x squared y, and all this is equal to 0. Okay. So this right here, this is what's known as the Bessel's equation, the Bessel form. Probably, and probably the feeling that that's probably overwhelming you right now is kind of like a feeling of what the heck is this? What the heck did we just do? Because you probably have never seen a Bessel's equation before this this point right here. So like I mentioned before, there's a lot of different we call them canonical forms in applied math where these certain differential equations or certain kind of integrals, they have kind of a well-documented solution. Okay. And so what we've done now is we've performed essentially a lot of algebraic and calculus operations to manipulate our original equation into this Bessel's form. Okay. And now that we've got this, we can state our solution very simply. And prepare to be underwhelmed, because the solution to the Bessel's equations is something called a Bessel function. Or I should say a combination of Bessel functions. So our solution y of x is equal to c1 times j1 function of x plus, or excuse me, j0 function of x plus c2 times y0 function x. For this j0, this is what's called a Bessel function of the first kind. And this y0 here is called the Bessel's function of the second kind. Okay. Bessel was not a very creative naming person, right? So I'm sure that's probably how he named his kids, right? Your first kid, second kid. The J and the Y probably comes from the names his partner gave the kids, or her partner gave the kids. I don't know if you know Bessel's a guy or a girl. Okay. So these are real functions. I'm not. I remember the first time I listened to this lecture. I'm like, this is all just he's just making this up. There's no way this is real. The Bessel's function is real. You can actually plot them, and so there's actually a built-in function in MATLAB for the Bessel's function. And so if you're curious about what they look like the following. And so if we look at J0, so this is a plot of the Bessel's function of the first kind. It looks like the following. It kind of almost looks like a decaying sinusoid. Okay. And the Bessel's function of the second kind looks like the following. Okay. So Bessel's function of the second kind actually has an undefined point at x is equal to 0, and then but it asymptotes at that point. So it looks like the following. So it comes down here, this, just like that. So there's our real functions, and so if you look up MATLAB Bessel's functions, you can see that you can actually call them, and you can actually plot their values as well. Okay. So the reason we kind of went through this whole song and dance, it is possible to solve this equation without the Bessel's functions. It's just the Bessel's functions kind of make it the most clean as a result. Otherwise, we'd have tons and tons of different terms floating. So we ended up, we spent, most of today again, kind of working through an equation mathematically. We end up with actually a very clean solution, but our solution here is only clean because Bessel made it clean. He made it famous to use these functions here. Okay. Now, of course, what we have here is what's known as a general solution, right? So even though we're making use of these Bessel's functions, it's still a differential equation. And so our next step that we're going to do on Thursday is we're going to apply boundary conditions to solve for our constant C1 and C2. Okay. But we'll do that on Thursday. We're just about out of time for today. All right. Any questions on anything we talked about today?
These take arguments like a trig function.
Yep. So you can plug in arguments to them like a value of x, and then it'll give you whatever function here's on.
I don't like the way like that one, the negative one is similar in all way.
Yeah. So the Bessel's function, the first kind, is defined from x equal to 0 to x equal to infinity. And then for the Bessel's function of the second kind, as long as it's 0 is not included in the domain, but anything greater than 0 and to infinity is defined for that.
And so now that can be.
They can be negative, or they can't take negative arguments.
The output to be.
Yeah. So actually the Bessel's function, the first kind, is an even function. So if we just plug in a negative, it just flips it on the other side. And I think second function as well, just that there's that singularity at x equal to 0.
Like an asymptote, I think.
Exactly. All right, so that's all we got time for today. So thank you guys for coming. On Thursday, we'll finish this up. And we'll see what this looks like. So thank you guys for coming. Hope you guys have a good rest of your day and see you Thursday.
What's it that for your chain, bro? That's a good question.
Sure.
I was working on. I think doing like some of the shapes come up a little off on it. Is there a way to edit it to like go to? These I did.
Yeah, so in those cases, that's probably a place where there's another branching vessel.
Yeah.
So that's kind of what you're getting. And so I would avoid segmenting in those places. So you can either delete that one. So the good thing about this one is that this looks like a fairly straight vessel right here. So it looks like you have kind of a lot of segmentations in there.
Yeah, because I know, would it be better, because I know we use threshold for them. Would it be better just to circle them if you can notice there's a branch?
Exactly. Yeah, so that was the other thing.
And
So,
then,
so one thing I would say is that, this looks like a little bit over segmented to me, especially with how straight and how
yeah,
the
so I
vessel
did it
is.
by 10.
Yeah, so this is, I'd say, probably the most common mistake people make with semester. So so for all the ones that are kind of sticking out, for now, I would say go ahead and just delete those ones.
Okay, because I noticed like some of these are right here where it's like the circles right there, and that's probably the branch.
Exactly. Exactly. And then in the future, if you have another branch that has something like this, you can just put a circle in there.
Oh,
And that's fine, because the threshold will pick these things like this up, but that's obviously, wrong. We know it's
And then-
not real.
and I remember you mentioned on one of the tutorial, there was one of these, I can't remember which portion of part of it was, you said to keep it in one,
Create a model.
the model, oh, the
When
model.
you
Yeah.
this
get
one?
there.
Yeah, so the model should just have one. So when you do this model here, just select all your segmentation.
Oh, instead of one. Oh,
Instead of, I think people have been doing one separate model for each
yeah,
segmentation.
but pass and ten segmentation are all gonna have.
Yeah, they're all gonna have their.
For sure.
Mhm.
Cool. Thank you.
Yep,
I received the two file. I start working on it.
yep,
And then this is the just a simple picture of the.
yeah, that's just a sample picture. So,
Okay, yeah, I can imagine because on the picture it not look like this. I'm like,
oh, yeah. So that's kind of what the ending model should look like. But, and so, this is just kind of give you an idea. Now, granted, it's,
it not look like this exactly right.
well, I mean, so everyone models a little bit differently the way
Yes.
you do the segmentation. So,
Yes.
don't stress out too much about getting exactly like this.
Okay,
But that's just to kind of give you an idea of the
Yeah.
shape,
yes.
how many vessels
And
there are
then-
gonna be.
I have a question
Sure.
because when I did the model.
Yeah.
So I make the curve like this, is the order already correct? But one of the order is like right, it's like right here.
Yeah.
So it has a big gap, it's not connected, but like have a big gap, so this one is,
Oh.
this one. This one is the daughter, like it's have a big gap between the daughter and the main vessel.
So the daughter vessel comes off right near the.
Yeah, right, yeah, right when I started.
Oh, that's strange. So this vessel doesn't come down any.
Yeah,
further?
no. Because when I grade, it have a big gap, or maybe I made a mistake, but it's like that.
Oh, that's weird.
Yeah, I was gonna ask
Because usually for the aorta, most of the branches come off kind of. the top
Yes,
of the
yeah,
arch.
that's correct. Yeah, they have some of them on the top, but one of them is like, it's.
I would maybe just ignore this one for now and see, because you know from the reference image how many of the other vessels are up here.
Yeah.
See, maybe this might just be an artifact in an image. I'm not sure what that would be.
Yeah.
But try to find the other vessels that come off the top of the arch and see if it matches a number that's.
Okay,
And
I
then
will,
this I would just kind of ignore.
I will try to finish it like Thursday.
Okay.
And I showed you the.
Okay, sounds good.
And I was gonna say too, with like when, because I'm doing the second one, but when there's branches, like daughter vessels, you want to emphasize more like segmentations on that portion, just to show the separation of it.
There shouldn't be any separation, so.
Not separation, but like separation from the main thing.
Oh, yes, yeah.
Okay.
Yeah.
So I'll do my laptop and it's so hard to see.
Oh, yeah. It might have a bigger.
But mine was like the big, so another daughter, it's just like small stuff over here, I
Yeah.
can see it, but this one is the big one.
Yeah, I'm not sure. This might just be an artifact in the imaging. I would just ignore this one, especially if it's coming off right here.
Yes,
Because there should only be one vessel that comes off apart,
yes,
unless there's something really wrong with this patient. Just, but from the image, it looks like a pretty normal patient. So
yes,
this is probably just, something weird in the image. So I would just ignore it.
that's it, not that, okay, just take care of the order.
Yeah.
Order.
Yeah.
Okay, I will try to finish by Thursday,
Okay,
yes, thank you very much.
yeah, no problem.
Oh, excuse me, Dr. Fern?
So you only